first thing that we're going to do is we're going to look at our log properties. Our log properties are going to parallel our exponential properties. Okay, so you're going to see some similarities with them. So the first thing that we've got to do is we've got to make sure that we have an understanding of how a log and an exponent go back and forth. That's what we have to do. And we're going to be focusing on that a lot today. So the definition of a log. So I have a log. Okay. I have a base when I have a log. And when I have that base, it is written kind of down as a subscript. Okay? That base is the same base for when I have an exponent. So x is what I'm raising to some power. So I have x raised to the b power. X raised to the b power. That is going to be my answer in a log. The answer to a log problem is an exponent. My answer to the exponent is my of. Okay, so I read this. Log base x of a equals b. That's how I read that. Log base x of a equals b. When I look at the exponent, my base is the same. My base is the same. Okay? Base is the same in your exponent and in your log. I know all of you are dying to know, but I have a new tip on my Apple Pencil. I know you were worried about that all weekend.
Yeah, I couldn't sleep.
I know, right? Okay. You guys love me. Okay. The answer to a log is the exponent. The answer, this has nothing to do with my tip. It's where I'm writing. The answer to the log is an exponent, or is the exponent. Okay? My of, or my a, is the answer to the exponential equation. Now, we're going to practice this. We're going to practice this a lot. But this is something that you need to be able to do. You need to be able to go back and forth. You need to be able to recognize the base, the exponent, the index. You need to be able to identify those things. And you're going to have to write this down about 3 times today. So just know that that's a big focus, is being able to go back and forth. Okay? Now, I need to erase this so we can do the rest of the stuff. Can I erase it? Mm-hmm. Okay. Here we go. So I'm going to keep the definition there for you. Okay. The change of base formula, it is used so that we can figure out non-traditional bases, okay? Now, You do not want to take this test without a calculator. I'm telling you that right now. Okay? You need a scientific calculator for this test. You don't want to not have it. You need to make sure that your scientific calculator has logs and has square roots. That's what you're looking for. So, the change of base formula, if I've got log base B of A, okay? When B is not 10, that my B looks a little like 10, doesn't it? Let me fix that. When your log or your base is not 10 or E or 2 or 3, it's a lot harder to figure out. The change of base formula allows us to do it more simply. Okay? So the change of base formula is where we take a common base. So in this situation, I'm going to write log base x of A over log base x of B. That's the change of base formula. And the x represents the same base. Okay? That's all that we have to think about, is that it's the same base. I would always use base 10. So you can think of this as log base A over log base B. Because when I don't have a base written down, it means base 10. That's what it means. Okay? So the x can be base 10 because we do a lot, base 10. Okay, so log base 10 of A over log base 10 of B. We're also going to talk about the natural log. The natural log is when we have a base of E. We briefly talked about E on Thursday. We will talk a little bit more about it today. So the change of base formula allows us to do that. Now we're going to get into these rules right here are used a lot. The quotient rule, the product rule, the power rule. They are used the most. Okay, so make sure you've got those down. The quotient rule, the product rule, the power rule. The quotient rule is when I am dividing. So I have log base A of C over D. I am dividing. Think back to when we divided exponents. When I had x to the 5th over x squared. What did I do with those exponents? X to the 5th over x squared. I subtracted. That's exactly right. I subtracted. I am going to subtract here as well. So this equals log base A of C minus log base A of D. That's what that means. So it's similar to our quotient rule with exponents. Now the product rule. If I had x to the 5th times x to the 6th, what would I do with those exponents? Add them. Okay? Same here. If I have log base A of C times D, that's going to equal log base A of C plus log base A of D. Okay. What I do with the power rule is I'm allowed to move my exponent. So if I have log base A of C to the x power, what I am going to do with the power rule is I'm going to take that x and I'm going to put it in front of my log. And then that's going to be multiplication. We use this all the time. So it's going to be x times log base A of C to the x. Nope, no x. I did that last class too. Sorry. I am taking the x, which is the exponent, and I'm putting it in front of the log, and I'm multiplying. Okay, these are the most common. They're the ones that we're going to use a lot. These are less common. They're a little bit of, you could figure it out without the property. And they can be called all sorts of different things. I was kind of looking at today to see, make sure I had the right one paired with the right one. And they're called all sorts of different things. So these are some things that I want you to be aware of. And this is a lot of the times if I've got the same base. So I've got log base b of b. That's going to equal 1. Okay? So let's think about that. So if I have log base 9 of 9 equals 1. If I rewrite this using exponents, that's going to be 9 to the first power equals 9. Okay? So if these are the same, if your base and your index are the same, the answer is 1. Always. Always, always, always. Okay? It's also true if I have an exponent there. So I have log base b of b to the x. Okay? My b is raised to the x. And do you see how my index and my base are the same? That is going to equal x. So let's think about that. If I had log base 9 of 9 squared, what that would mean is 9 squared equals 9 squared. So when I've got a base and then the base of the exponent, when they're the same, the answer is just that exponent. Okay? The next one's just weird. Okay? So if I have b and it's raised to a log power, okay? Your bases are the same. That's b to the log base b of k equals k. I do an example with it, but it's just not something you see that often. Okay? So the first two, I don't want to say that they're common sense, but they're things you can figure out pretty quickly if you knew the definition of a logarithm. Okay? If you knew the definition of a logarithm, you can figure these out. Okay? And again, I think this one's just a little bit weird. It is useful and important, but it's not something we're going to use a lot. Property of log equality is important. Okay? Property of log equality is important. We are going to use that quite a bit when we're solving equations. It's very similar to how we solved exponential equations. Do you remember if I had a to the x equal to a to the y? What could you tell me? X and y are equal. That's exactly right. X and y are equal. My bases are equal. That means my exponents are equal. The same is true here. The same is true here. Log base a of c equals log base a of d. That means that c is equal to d. Notice that your base must be the same. If these bases are not the same, it doesn't work. Your bases have to be the same. Your bases have to be the same. Are we ready to put this to work? We ready? Can I move off this screen? I know that's a lot of writing. Yes? Okay. So, this is our first one. This is the question that you're going to ask yourself. What power do I raise to in order to get 32? Okay? So this log base 2 of 32, I'm saying 2 to some power is going to equal 32. And I have to figure out what that is. Okay? And sometimes you can figure it out, and sometimes you need logarithms to figure it out. Okay? This one we can figure out. 2 times 2 is what? 4 times 2.
It's 5.
Okay? Times 2. We're at 16. Times 2. 32. Okay? So 2 to the 5th power is 32. Okay? 2 to the 5th power is 32. Okay? Now we're going to do the next one. What power do I raise 7 to in order to get 1? It's 0. It is 0. Okay? So 7 to the 0 power equals 1. Okay? Now we're going to do the next one. So we're doing log base 36 of 6. It's not 2. I'm just telling you right now, it's not 2. What power do I raise 36 to in order to get 6? So this is going to be 36 to some power. It's going to give me 6. It is 1/2. What is the relationship between 36 and 6? What's the relationship? It's the square root. Okay, 6 is the square root of 36. We talked about rational exponents on Thursday, and that's what this is. 36 to the 1/2 equals 6. Okay. Now I've got the natural log of E. Okay, when I have the natural log of anything, okay, and that's ln. I can have the natural log of 10. I can have the natural log of 50. I can have the natural log of anything, okay? When I have the natural log, and we're going to rewrite this, when I have the natural log of x equals y, the natural log has an assumed base of e. Okay? It's an assumed base of e. And this would be e to the y power equals x. That's how that's rewritten. Now, e has a value of 2.718, but it goes on forever. Okay? E goes on forever. It is an irrational number just like pi. E is an irrational number just like pi. Okay? So 2.718. And then it goes on forever. You are going to want to use the e on your calculator. You're going to want to use that, the e on your calculator. Now, e is, thank you, that'd be good. E is used for population growth. Okay, we talked a little bit about it on Monday. It's used for decay in biology. So if you've got a radioactive material, that's got a half-life and it decays over time. Okay, E is used in that. The most common, and what you'll see the most, is compound interest. Compound interest on our cars payments, our credit cards, and if we're really lucky, whatever money we have in the bank. Okay? So compound interest is how that's figured. And anytime you see population growth, decay, or compound interest, we're using the value E. Okay? So, up here, where I've got the natural log of E, what is my automatic base when you see ln? And that's an ln. I had a student that did in for a long time, and she couldn't understand why she kept getting her homework wrong on this electronic thing. I felt so bad for her. I said, why are you typing in? Okay, that's an ln, natural log. What's the base? What's the base in all natural logs? E. So e to what power is going to give me e? 1. Okay, so it's e to the first power gives me e. Okay, now when you see a log written with no base, okay, sometimes you'll see log. Okay, the assumed base with that is what? Does anybody know? 10. Okay, so this would be 10 to the y power equals x. 10 to the y power equals x. So, if you see ln, your assumed base is e. If you see log with no base, your assumed base is 10. Okay. Can I move on? Okay. Now we're going to use the laws of exponents. Okay, the logs of exponents. Now, oh, I didn't erase the answers. Sorry. Usually I do the answers in red, so. Okay, I want you to look down at the bottom. I have a to the x equals y. Okay, my a's are the base. My x is the exponent in my exponential equation. So x in a log is equal to x. My y is the answer to the exponential equation. So here's how the y's go. So we've got you want to be able to go back and forth. You absolutely want to be able to go back and forth. So log base 3 of 5 equals y. So I'm going to write that as an exponential equation. That's going to be 3 to what power? And what's it going to equal? Excellent. Okay? We're not solving these. We're just rewriting them. Okay? My next one. What is my base here? 10. Okay? There's an assumed 10. What power am I raising it to? And what does that equal? 1,000. That one you could figure out if you wanted to. Anybody know what z is? 10 times 10 times 10. It gives me 1,000. So what would that be? 3. So 10 to the third is 1,000. Good job. Okay, what's my assumed base on the last one? E. And it's to what power? And you could figure that out, but you're going to have to do it as a log. That's you'd have to solve it as a log and not an exponent. Okay, let's go the other way. Can we go the other way? Okay. So, here you've got it again. Log base a of y equals z. Y is the answer to the exponential equation. A are your bases, they stay the same. Z is your exponent. So when you are solving a log equation, you are trying to figure out what the exponent is of the base to get that number. And a lot of times, most of the time, the base you're dealing with is 10 or e. So we're rewriting this as a logarithm. So I'm going to have log. What's my base? My base is not c. N is my answer. My base stays the same. What's my base and my exponent? B. Okay, so this is log base b of n equals my exponent. Okay? This is my base. That's my base right there. What's my base in my next one? Good. This is log base 1/3. What's my index or my of? And what does it equal? Good. Okay. My last one, what's my base? 8. Good. Log base 8. of 15 equals x. Okay? You just got to practice those. You just got to practice those. Now, students typically do okay writing them back and forth. They usually do okay with going back and forth between the logs and the exponents. Okay? Now we're going to start using the rules, the properties of logs. This is where sometimes students start to struggle, especially the more complex the problem. So we're going to hit these on Thursday, on Tuesday. We're going to hit them several different times. Okay? So I've got log base 4 of 3 minus log base 4 of n. So when I am subtracting two logs, I can rewrite that as a single log, but what's happening with the 3 and the 9?
They're not subtracting.
They are subtracting when they're written as multiple logs. Look at your properties. When I am subtracting two logs, you're dividing. Good. Okay, so this is going to be log base 4 of 3 over 9. Can that 3 over 9 be simplified?
Yes.
Good.
Let's see what happens.
It is okay. It is that time of the semester where, we're all a little bit crazy, and that's okay. Okay. There's a couple of things going on here. I want us to deal with the number right here and here first. Okay? When I've got a number in front of a log like that, where is that going? It's going to go above the 3x. Now, that 4 belongs to the 3 and the x, and that is something that students miss. Okay? So this is rewritten as log base A. The 3 and the x are raised to the 4th power. Okay? The 3 and the x are in that index. Both of those are raised to the 4th power. Okay? Where does the 5 go? To the y. Okay. Now, I am adding two separate logs. So if I rewrite it as one log, what's happening with the 3x to the 4th and the y to the 5th? Multiplied. Excellent, excellent. Okay, so I have log base A of 3x to the 4th times y to the 5th. Now, can I simplify 3 to the 4th? It's not too bad. 3 times 3. 9 times 3. 27 times 3.
You want to do that?
Yeah.
81.
81. You will be allowed to use your calculators. Do not take this test without a calculator. Okay? 3 to the 4th power is 81.
So you keep the 4x?
Yes, because that 4 belongs to the 3 and it belongs to the x. So you could rewrite that using exponent properties, 3 to the 4th, x to the 4th. So good question. Good question. Okay. Okay. Let's do the next ones. Okay, now we're going the other direction. Log, what's my base with this log? 10. Log base 10 of C divided by D. So when I rewrite this, my base is going to stay base 10. I don't have to write down base 10. But what am I doing between the two logs? Good, because of my quotient property. Okay. Now, this one, we've got a couple of different things going on. So I want us to start in the numerator. I have log base 6 of x. And what is happening in my original log between x and z? Multiplication. So what do I do when it's multiplication? Add them. So I have log base 6 of x plus log base 6 of z. Now, what am I doing with the y to the third? I'm dividing, so what do I do with this separate log? Subtract. So I have log base 6 of y to the third. Now I'm not done. Why am I not done? Good, that 3 goes in the front. So I have log base 6 of x plus log base 6 of z minus 3 log base 6 of y. Now, I'm going to put a different problem up here, and I want us to talk about it. What if this problem was written as log base 6 of x over z times y to the third? Okay? So typically students say, well, Alicia, you're multiplying z and y to the third together, right? Okay, but where are z and y to the third? In the denominator. Now, let me ask you a question. Based on my exponent rules, am I allowed to rewrite the z as z to the negative 1? Could I do that? Is that allowed based on negative exponents? Yes. Okay? So then I would have y to the what? What? If I moved it to the numerator, what would I have? Negative 3. Now, I am multiplying x times z to the negative 1 times y to the negative third. So I'm going to add all those together because I'm multiplying. So I would have log base 6 of x plus log base 6 of z to the negative 1 plus log base 6 of y to the negative third. What happens to those exponents? Where do they go? In front. So this becomes log and minus log. Good. Good. Oh, minus 3. Thank you. Okay. Okay. So I want you to think about that. So if we go back to my original blue equation, I have log base 6 of x over z y to the third. If it's in the numerator, I'm going to be adding them. If it's in the denominator, what am I going to be doing? Subtracting. Okay? So you don't have to go through that process. I just want to show you why. Students, when they've got more than one thing in the denominator, they don't realize that you are actually subtracting everything that's in the denominator. That is a very common mistake. So, looking at this again, we can rewrite this log base 6 of x minus log base 6 of z minus log base 6 of y to the third. Sorry, I know I'm running out of room. Okay? Okay, and then I'm going to write this down here, minus 3 log base 6 of y. Okay? So what I did on top was just to show you why. Yes?
if you have more than one in the denominator, you're always going to be subtracting, even if they're multiplying together.
Yes.
Okay.
Yes.
Got it. Thank you.
That is an excellent summary. Thank you. Yes, sir.
I have a question about the numerator.
Yes.
If you have a number and a variable, do you separate them? Like Adam. Would you go log base 6 of 3 plus log base 6 of x?
Yes.
You would?
Yes, you would.
Okay.
Yes, you would. Thank you for asking that question. And that's going to be a key point on Thursday when we're solving equations, because I can find out what log of 3 is. I can find out what it is. Okay. Now, I think we're doing change of base formula. Yes. Okay, can I go off this screen? Okay, change of base formula. Change of base formula. Okay, I'm using base 10 as my common base. I'm going to use base 10. So the way I figure this out is log base 10 of 4 divided by log base 10 of 3. Now, your calculator will only do what you tell your calculator to do. Okay? That's how it works. Your calculator will do what you tell your calculator to do. Okay? So, make sure you are telling your calculator to do what you want your calculator to do. So, this is how your keystrokes. You're going to put the numerator and the denominator in parentheses. That is a habit that you want to get into now. So then you are going to have parenthesis log. As soon as you hit log on your calculator, what pops up? Another parenthesis. So you are taking the log of 4. You've got to close that parenthesis with the 4 and close the parenthesis with the numerator. And if you don't, your calculator is going to give you the wrong answer because you put it in incorrectly. So when you are doing logs, you are going to have a lot of double parentheses. Okay? Then we are dividing by log, and you want a parenthesis here. I am about to lose it with this door. It doesn't stay cracked. I've got a voice that carries, and so I have to keep the door closed. Then I am dividing by, you've got to start your parentheses, log of 3. If anytime you hit log on your calculator, it shows a parenthesis. And then you've got to close the parenthesis with the 3 and close the parenthesis for your denominator. Okay? Tell me what this is. I want you guys to do it.
I got 1.26.
Okay, 1.26. Let's go a few more. 1.26.
185.
Okay, 185, so that would round to 9, right? Okay. So, let's do the next one. Log of 40 over log of 5. Make sure you are putting your numerator and your denominator in parentheses. That is so important habit. It's a huge habit to get into before Thursday. Okay, so then I'm going to have parentheses, log 40, double parentheses, divided by log parenthesis 5, double parentheses. Those are your keystrokes. And I don't know the answer. I think it's 2 point something.
It's
2.292. Is that rounded correctly?
Yeah, there's a 0.
Okay. Okay? Okay. Lots of different things about logs. Now we're going to look at the graphs. We're going to look at the graphs. Okay. What I have here is I have e to the x in blue, and I have the natural log of x in red. They are inverses of each other. Okay? And that's what exponents and logs are. They are inverses of each other. Okay? So, when we talked on Tuesday, we talked about this point 0, 1. We talked about the point 0, 1. And let's think about why that point's important. If I had e to the 0 power, what would I get? 1. Okay? If I have any base to the 0 power, what am I going to get? 1. That's why that point is so important. Okay? So that point, we're always thinking about where is that point going? What direction? What am I moving it? We also talked about the asymptote. What is the asymptote for e to the x? 0. Is it y equals 0 or x equals 0? Y equals 0. Good. So here's my asymptote right here. So my graph approaches 0, but never gets there. Okay? It never touches 0. It just approaches 0. So my asymptote to this is y equals 0. Okay? Then, if I had something in parentheses with the x, it moved left to right. If I had something outside the parentheses, it moved up and down. Okay? Now, when we start talking about logarithmic graphs, that's going to change. The first thing that's going to change, yes? It's the x-axis. It's the x-axis, but it's y equals 0. All horizontal lines are y equals. Yeah. Okay? My point changes. It's the inverse of 0, 1. So what is it? 1, 0. That's going to be the point we look at. Where is that point going? Where is 1, 0 going? Okay? Now, my asymptote is now a vertical asymptote. It is the y-axis. And how do I write the y-axis as a line? X equals 0. Okay? So these are parent functions, and these parent functions are inverses of each other. If I drew a line of y equals x right here, they would reflect across that. That's what an inverse function is. They are inverses of each other. Okay. Now, let's go through this. Let's look at each one of these. I would probably take some pictures of the next couple of graphs, okay? Because you're probably not going to be able to sketch them, and so taking pictures is reasonable. I would wait until I've finished writing everything, though. I think that's a better way to do it. Okay. So, here, what I have is I have log of x, and I have log of x minus 1 and log of x plus 3, and the plus 3 is outside. Okay, so let's look at my red graph. My red graph, my point is right here. So the point that I'm focused on is 0. Nope, it's not 0. What is it? It's 1, 0, right? What's my asymptote for the red graph? What's my asymptote? X equals 0. Okay. When I am inside the parentheses with the x, which direction am I going? Up and down or right to left? Right to left. Am I true to value or opposite value? opposite. So x minus 1 puts me to the right or to the left? To the right, okay, because I'm going plus 1. So there's my point. So my point moved over 1. So my 1, 0 moved to 2, 0. Okay? Where is my asymptote now? X equals 1 is my asymptote. Okay? X equals 1 is my asymptote. Now, my green function has the plus 3 outside. Okay, so what's it going to do? Up, down, or left to right? Up, down. Okay, so here's the point that I'm looking at, and it's going to go up 3. 1, 2, 3. Okay? So that point that drives everything is now 1, 3. What is my asymptote, though, when I'm moving up and down? It stays at 0 because I'm just moving up and down. Okay? So my asymptote is driven by my right to left movement. Okay? So I'm going to say that again. Asymptote driven by left to right movement with logs. Now, we didn't talk about this on Thursday, but the exponent, the exponential function, what drove the exponential function's asymptote? No, you're fine. Go ahead. Anybody? It's the up-down movement. Okay? So the right to left movement drives where your asymptote goes with the logs. When you're talking about an exponent, an exponential function, so this one, e to the x, my asymptote, I'm going to write this here, asymptote driven by up-down movement for exponential. Okay? Asymptote driven by up-down movement for exponential graphs. Okay? For logarithmic graphs, the left to right movement drives it. Okay, can I move off this screen? Shay, do you need some more? I've got some right here.
Sorry, I'm not full today.
Okay, can I go to the next one? Yes, I'm good. Okay, now we're going to look at reflection. Now we're looking at reflection. Okay, we're looking at reflection. My red graph is my parent function. That's my parent. That's my parent function. Okay? Log of x. What's my base in all of these? 10. Okay? My base is 10. So the red is my parent function. My blue graph is when I reflect across the y-axis. Okay? And before I leave my parent function, I'm going to write this point down, 1, 0, because that's the point that we want to watch. That's the point that we want to watch. My asymptote when I do the reflection is still x equals 0. Okay? My asymptote is still x equals 0. My blue graph is reflecting across the y-axis. Notice where the negative is. Where's the negative? It's with the x inside the parentheses, okay? So this is when we reflect across the y-axis. Okay? The point to watch. What does the point to watch become? What does it become? Negative 1, 0. So you're going to do that reflection first. Do that reflection first. What's my asymptote, though? X equals 0. It's still x equals 0. Now my green function, I have the negative outside in front of the log. Okay? What did it reflect across? The x-axis. Okay? Where's the point to watch? It stayed the same, didn't it? It's still right here. Okay, so 1, 0. And what's my asymptote? X equals 0. Okay. Now, are we ready to put some of this stuff together? I would go home and I would do number 9 on your project tonight.
Okay.
While this is all fresh. Maybe even number 8 and 9. Okay, can I go to the next one? Okay. So, 3 to the x is just my exponential function so that you can see the inverse. We are focusing on the red function, log base 3 of x. That's what we're focusing on. Log base 3 of x. My point here in log base 3 of x that I'm watching is this point right here. Okay? So I've got 1, 0, and my asymptote is x equals 0. Okay? The 3 to the x is just to show you what the inverse is. Okay. So I want you to reflect across the x-axis, move left 4, and move up 3. That's what I want you to do. Reflect across the x-axis, move up 4, move left 4, and then move up 3. Try to write that down and then pull out Desmos. My son took the Acuplacer at the community college today. And so my husband and my son have been texting me for the last hour and a half. And I'm like, I'm in class. I'm like, you guys know my schedule. But my husband has admin time on Tuesday morning, so he just thinks I should be at his beck and call. And I'm like, it doesn't work that way. I'm in class. Okay. Any ideas? Where do I put the negative if I want it to reflect across the x-axis? Where do I put the negative? On the outside. Let's see if we're right. Okay, where did I put the negative?
On the outside.
On the outside. Now, when we reflect across the x-axis, the point to watch stays the same. You see that? The point that I'm watching is 0, 0, 1. Okay, so when I reflect across the x-axis, I put the negative on the outside of everything, and my point to watch stays the same. Okay, now, if I want to move, I keep forgetting what I said.
Left 4.
Left 4. What do I do?
Negative 3 on the inside. Negative 4, sorry.
So which way am I moving? Left 4. So it'll be what? It'll be plus 4. Yeah. Okay, and am I moving up or down 3? Up 3, so where's it going to go? On the outside. Okay, any idea where the asymptote is?
Oh, wait.
The x movement dictates the...
It's definitely going to be
No,
2.
no, the asymptote, it's a line.
No, it's going to be a negative 5. No,
Let's just look at it.
dang it, I guess wrong. It's negative 4.
Okay, let's look at this. Okay, the red is my original function. The red is my original function. Okay, so I started right here. I reflected first. When I reflected, did it change the point to watch?
No.
No, it didn't. I reflected across the x-axis. It did not change the point to watch. If I had reflected across the y-axis, it would have. But this one didn't. So my point to watch stays the same. Now, I want to go to the left 4. So I'm going to the left 4. So it's opposite of value. So to move to the left 4, I have to say plus. So I have 1, 2, 3. Whoops, is that 4 or 3? One more. 1, 2, 3, 4. There we go. Then I'm going up 3. 1, 2, 3. Whoa. Okay, there's my point to watch. Okay? Now, my left to right movement dictates my asymptote. So on my red graph, my asymptote is x equals 0. What is it on this graph, the purple graph? Nope, it's not y equals. It's x equal, it's negative 4. Okay, it's right here. So, okay, look right here. So my red point, it moved over 4. But where did my red point start as far as an x value? It started at 1. Okay, where is my asymptote start? Where's my asymptote starting? It's at 0. Okay, so here's my asymptote. Okay, so it's moving 4 as well, but it started at 0. So here is my asymptote, right there. Yes, and so my asymptote is x equals negative 4. Yes? With logs. Yes, with logs. Okay, with exponents, it's going to always be related to the y. Now, when you reflect, it gets a little tricky, so just make sure you're looking at the graph correctly, but yes. Okay. Are we going to be okay? Yes, we will. We're going to be fine. Okay, it's not a terrible idea to do problems 8 and 9 tonight on your project.